Let's continue with our discussion on introduction to algorithms for data mining and machine learning. So far, we studied introduction to optimization and mathematical methods foundations. And then in this chapter, we are ready to continue to do more deep dive on the optimization algorithms. Just be aware, almost everything is optimization, or almost everything needs optimization. If you think about it, you could maximize efficiency, accuracy, profit, performance, sustainability, or you could minimize cost, wastage, energy consumption, travel distance, or time, minimize the CO2 emission, minimize the impact on environment, etc., etc. And then let's take a look at what is maximize. What is a mathematical optimization, which you already know, right? So we're trying to minimize or maximize a specific fx, and then subject to multiple equality or inequality constraints. It would be hix equal to 0. It could be one set that I can go from 1 all the way to m, or another set of inequality constraint gjx less than equal to 0, j equal to 1 all the way to n. And in terms of objective function, if we have multiple, could be f1x, f2x, etc., then we call it as multiple objective optimization problem. Apparently, so far, we only look at m equal to 1, that is single objective optimization problem. So here are the key components for optimization. What you do is you come back with an algorithm, and this algorithm would be able to handle constraints, and then you can evaluate objectives by using those algorithms that handles constraints, and then try to select solutions from your evaluation of the objectives. These are the key components for optimization. We discussed this in Chapter 1, the essence of algorithm. So K is really whether we are able to come back with a better solution vector or point xk plus 1 that can be used to modify or replace our original solution of xk. And then different algorithm essentially would be different ways for generate new solutions. There are two classes of optimization algorithms. One class is called deterministic. The other one is stochastic. Just at high level, for deterministic type of solution algorithms, it could include Newton's method, NewtonRaphson, hill climbing, steepest descent, or least square type of approach. And then linear programming, conjugate gradient, interior point type of deterministic optimization algorithm. So linear programming is something that's very popular, and essentially the constraints and objectives are all linear combination of constraints, essentially linear constraints. For stochastic algorithms, it could involve generic algorithms, colony optimization, particle swarm optimization, differential evolution, cuckoo search, firefly algorithm, bat algorithm, flower pollination algorithm, etc. So just be aware of some of these solution algorithms. So you probably already realize, wow, that's a lot, right? It's actually indeed a lot of different optimization algorithms, and these are only the key algorithms that actually are listed here. Steepest descent or hill climbing, which is also called gradient-based approach. You probably already learned this methodology. That is to say, use gradient or derivative information. It is very efficient for local search. Newton's method actually indeed is something that we already discussed. Remember that we said for a polynomial px equal to 0, its roots can be computed by xk plus 1 equal to xk minus pxk divided by p prime xk. And then it starts from x0. P prime x is the first order derivative of px. Usually it shouldn't be 0. So for minimization and maximization of univariate function of fx, we know it is in order to find the solution, it is equivalent to find the roots of its gradient of px or f prime x equal to 0. So now you know that xk plus 1 equal to xk minus p xk divided by p prime xk essentially is the same as xk minus f prime xk divided by f double prime xk, where we have also used f double prime x, implicitly assuming that these derivatives exist, meaning the first order derivative and the second order derivative as well. So this is a very similar example as what we discussed earlier, but we could very quickly go through as well. So we have this function fx. We know that its global minimum is at 0, f min equal to 0 with x star equal to 1. Let's take a look at how we can use Newton's algorithm to get this. Xk plus 1 equal to xk minus f prime xk divided by f double prime xk. And then we start with the initial solution that is a, any value. Remember earlier we actually specifically started with some solution, but here we say let's start with some number a. A is larger than 0, and then we know that f f prime x is 2x minus 2, and then f double prime x is 2x, and then 2x0 minus 2 double prime is really 2, right? 2x, one more derivative, that's 2. So 2x0 minus 2 divided by 2, that's what we have. And then because we know the previous solution xk, so that we have a minus 2a minus 2 divided by 2 equal to 1. This reaches optimality in a single step. This shows that the algorithm is very efficient. So this is however, this is really a special case just because the objective function is convex and quadratic. In general, it needs more steps, but still very efficient. Just be aware of this two key term here. One is convex that we already discussed in chapter 2, and the second is quadratic second order, right? Even though Newton's method works really well, but it does have serious drawback. The final solution may depend on the initial starting point of x0. In some cases, solutions will not converge at all. So let's demonstrate this dependency of the initial solution using a specific example. Let's look at this example. So we have function of x squared and exponential of negative x squared. It has two maxima. One is x is 1, the other one is x equal to negative 1. And one minimum. That actually happens at x star equals 0. Let's take the first order derivative. F prime x is 2x. Oops. So in order to take the first order derivative, you have to take first order derivative of this. And then a first order derivative in terms of this. And then what I'm saying is you should do first order derivative of this times that plus x squared and the first order derivative of that, right? And then once you do that, by simplification, you come back with this: 2x times 1x squared times e powered by negative x squared. And then continue with the second order derivative. Now you have 3 terms. You have to do that by part again, right? You take the first order derivative of this times this whole thing plus first order derivative of this times those two plus first order derivative of this times the other two. And with simplification, we got f double prime of x is that. Once we have that, we can leverage Newton's iterative formula, and then we come back with xk plus 1 equals to this simplified version of the relationship. We know that exponential of this negative xk squared doesn't equal to 0. That's why we could cancel those two. If we start with x0 equal to 0.8, what we got is 1.008. And then we also get x2 equal to close to 1, x3 close to 1, which is very close to our x star equal to 1.0. How about from x equal to 0.24, we can get negative 1 very easily. But if we use x0 equal to 0.5, we have x1 3.5, x2 3.67, x3 3.82, which gradually moves towards infinity. In this case, the iterative sequence becomes divergence. It never reaches optimal solution of 1.0. So just give you an example on the possibility of the impact of initial solution. It's a very efficient algorithm. However, sometimes if you don't have the proper initial solution, you could end up with inefficient process. For higher dimension Newton's method, for a multivariate function fx, and then x is x1, x2, all the way to xn in the n-dimensional space, and then the maximum or minimal occurs at f prime x equals 0, which we already know. That is, the optimality is reached at the roots of the stationary or critical condition that satisfies f prime x equals 0. And Newton's method is this expansion, that is to say, if we have this Hessian matrix, and then we can use Hessian matrix to come back with this relationship, and then this algorithm is called Newton-Raphson Method. So you could take first order derivative in terms of each individual partial first order derivative in terms of each individual x. And then you could define Hessian matrix, that is, remember that the diagonal would be in terms of each of the individual variable, second order derivative, and off diagonal is really partial order derivative in terms of x1 and x2, x1 and x3, x1 and x4, all the way to there for the first row, and same thing as the first column as well. And then this Hessian matrix inverse, so you can see that xt plus 1 is xt minus Hessian matrix inverse times first order partial order derivative. So this method is now called Newton-Raphson method. So by convention, T is the iteration counter, and earlier we used K as well. Could be xk, could be x powered by k. This power has a bracket there. Occasionally we use x powered by k just to be aware, unless there is a confusion on the exponent, right? Otherwise, you could use x powered by k. These are the list of the possible notation for different iteration of solutions. Calculation of Hessian matrix H for each step can be computationally very expensive, especially for higher dimension problems. So we should try to use, try to avoid use of H whenever possible. Now, there's a new approach that's called, it's a new approach in terms of build upon Newton's method, called QuasiNewton method. So if H is replaced by I, identity matrix, then we have xt plus 1 equal to xt minus alpha I, and first order derivative of fxt, which is xt minus alpha in terms of first order derivative of fxt, and then xt plus delta xt. And this delta xt is the minus alpha first order derivative. So now you see that this gradient idea and the step size idea. And alpha is between 0 and 1 is a parameter that controls the step lengths, and alpha should be related to the eigenvalues of H at each iteration, but we usually set it to a fixed value. And you need to find new moves by gradient. You need to find the direction. You need to have a specific step size, and then start from the previous solution xt or current solution of xt, move to somewhere with certain step size and gradient direction, come back with a new solution xt plus 1. So this increment or step is delta xt, which is minus alpha times gradient of function at xt. So it moves along the negative gradient direction for minimization, lead to the steepest gradient descent method. In machine learning, the alpha is often called learning rate. This is very similar to, instead of use very similar, I should be saying that it's very useful in the neural networks and deep learning. This alpha itself is the learning rate, and it's not only just in deep learning or neural networks. In many other machine learning algorithms, alpha is being used as a learning rate. And then just be aware, the dimensionality of machine learning problems is very high. Even the calculations of gradient can be very expensive. Therefore, the components of gradient may be computed sparely to save time. For example, stochastic gradient descent and momentum-based methods such as atom optimizer are often used in deep learning. Okay, just give you some high-level concept here, but for now we're not there yet. At one point, we're going to discuss how some of this approach are being leveraged in the deep learning context. Another algorithm called line search. To find the local minimum of the object function of fx, what we are trying to do here is try to search along a direction sk with an adjustable step size of alpha k, so that Kc alpha k equal to f xk plus alpha k sk. So that we also try to make sure that this function f xk plus alpha k sk decreases as much as possible, which depends on the value of alpha k. In other words, what we're trying to do is we find a right step size so that we try to move our objective function as much as possible, decrease it as much as possible. And then Wolf's condition is fxk plus fk times sk should be less than or equal to fxk plus gamma 1 of this first order derivative with specific step size. And then this particular quantity that's on the as a calculation result, this condition should be satisfied. That is, these should be larger than or equal to this quantity on the right hand side. And gamma 1, gamma 2 should be between 0 and 1. They are algorithm-dependent parameters, or in many cases, machine learning algorithms, we call it hyperparameters. And then you can set gamma 1 and gamma 2, and then try to leverage line search algorithm to update their new solution. So this is the algorithm itself. Now you see that we are getting into more ways of all of these algorithms. Next one that we that's coming up is called stochastic gradient. So in many optimization problems, especially in deep learning, the objective function or risk function to be minimized is as the following form. It's kind of have some sort of flavor of um, linear regression, right? But it's not quite. If here you see that in, not sure if you know high level what is deep learning or what is neural networks. What we're trying to do is we come back with a set of weights. Those weights would be help you to come back with a relationship between the input and the output. For now, you just have the high level, you know what I'm referring to. Maybe I should still give you a specific example. Let's see. So I'm leveraging this space. Simple speaking, right? What we're trying to do is we'll have a bunch of input. Usually what we call is an input layer. It's one column input layer for individual input. This could be x1, x2, x3, x4, etc., etc. And then we also have something called hidden layer. And then we do have something as our output. Let me use a different color. So these are the x, this is y, and then whatever in between is something that we don't know. We call it hidden layer. So what we are trying to do is we have a bunch of we can come back with a bunch of relationship or linear weights. Some of them can be 0. Let's call it W, say W1, W1, W2, etc., right? To be more precise, maybe two-dimensional, we should be calling it as W11 for this particular one, and then it would be W12 for one more. That would be W12, etc. So what we're trying to do is we come back with these weights. We're trying to figure out what would be the proper weights so that we find the relationship between the input and the output and the hidden layer and the output, so that we are able to know the relationship of x and y. Again, we're trying to figure out this weight so that using these weights with the input, we have an output, and then this output compared with the true value of the y, we're trying to make sure that this output is not too far away from that true value of y. That's really the idea, right? Now you know some sort of y average versus some sort of linear combination of xi and w. W is indeed these weights. Input, some sort of linear combination of the x and w, come back with an estimate of y, minus yi average squared, and then sum them up, and then use 1m divided by m to get the average. So we're trying to minimize the minimize something called objective function or risk function is to minimize this quantity. See, here is really a high level, just to give you 1,000-feet view of what is neural networks. And then, of course, what is deep learning? Deep learning is built upon neural networks that have multiple hidden layers, especially when layers have a lot of layers, more than 50, for example. Then we call it deep learning. So here, W is a parameter vector. It's a weights in artificial neural networks, which is the neural networks that I just discussed. And then YR bar is a target or real data. It's really not average. It's really, it's really the target or real data. So again, use a linear combination of X and W to come back with the estimate minus the real observation and squared. That's the idea. And the UIXI are the predicted value based on the input XI by a model. By a model here, meaning a trained neural network. Then in this framework, what you can do is you use current weight to update to get a new weight. And then our current weight is dependent, new weight is dependent upon some sort of gradient and the step size. And then here, this is the learning rate, and it requires m gradients, expensive if m is really large. And then to save computation, the gradient is approximated by 1 instead of m values. And then this would be simplified in this relationship, and the beta larger than 0 is a hyperparameter, which can also set be a fixed value. Now, this is really a high level discussion. We are going to come back with this in further detail, but at least at this moment, you should know what is gradient descent, what is stochastic gradient descent, and then what is neural network or deep learning at high level. Okay, let me clear this, and then we can move on. Gradient-based optimizers, including stochastic gradient, gradient descent algorithm, are widely used in machine learning. However, they can have strong oscillation for objectives with narrow valleys. Just be aware of this. And the same thing as you saw previously. The main step in gradient step optimizer is update the previous solution with gradient and come back with a current solution. Moment-based methods can be considered improved variance to damp potential oscillations. The main additional step is to use something that definition of a mu k plus 1. It's very similar to what we saw there. And then once you have a mu k plus 1, instead of using original xk minus this, now becomes original xk minus mu k plus 1 to come back with your new xk plus 1. Typically, gamma used is 0.9. So this is another different optimizer called RMS prop. RMS prop optimizer has the same type of concept. So that you have this derivative concept there, and then to update concept, and then this square root is a root mean squared error, and then you have a running average formula, and so that you can update. So and then just a little bit background, RMS prop optimizer was introduced by G. Hayton for machine learning, which has some similarity to ADA delta with gamma equal to 0.9. The weight update becomes this relationship. Okay. Adam optimizer. Now you see a lot of optimizer that's named by different people. But at the end of the day, it's just iterative process. And this one is specifically being implemented in TensorFlow. Just something that you should be aware. And then for now, actually, we'll stop here. We discussed a lot of gradient-based optimizers. And we'll come back with more gradient-free optimizers. Thank you.